Okay, so hello everyone. So welcome to our this week Rugged Efficiency AI seminar. And today we're very glad to have the Professor Yuke Wang from the Rice University. And right now he's also working in the Amazon to give us this talk titled Intelligent Software in the Area of the Deep Learning. And Professor Wang is the incoming assistant professor at the Rice University CS department. And he's currently the postdoctoral scientist in the Amazon AWS. And he obtained his PhD from the University of the Santa Barbara. And his research interests include the system and the compiler for the deep learning and the GPU-based high-performance computing. And his projects cover the graph network optimization and the acceleration on GPUs. And he has published more than 20 publications in the top-tier conferences, including OSDI, S+, ISCA, ATA, ATC, PPOP, supercomputing, and so on. All of the very prestigious system and architecture conferences. And his research.com has been adopted for future research in industry, like the NVIDIA, AutoMail, and Alibaba, and academia like the Washington Pacific Northwestern National Lab, and so on. And he's also the very prestigious NVIDIA graduate fellowship recipient in the 2022. So now let's welcome Professor Wang to give us this talk.
Thanks, Professor Yuan, for giving me this kind of introduction. So hi everyone. So today I would like to introduce you my research, basically the systematic approach for efficient and scalable deep learning. So let's start with some like a basic background on myself and about me. I have got my PhD recently from UC Santa Barbara, and also there's some industry experience where I have been working in this kind of big tech companies. And also my research objective basically is try to facilitate efficient, scalable, and also the secure deep learning in the future. And before we dive into details, let's have a short recap of the trend of the deep learning algorithm and also the hardware. So the first part we want to focus is that over the recent years, what happens to our deep learning model as well as what happens to our hardware devices. So let's take a look at the model size. When we take a look at the recent trend of this kind of model, what we observe is that the overall size of this kind of model are growing larger and larger, and they are trying to accommodate more parameters and thus more training efforts. And this kind of typical example are here, like the Llama, Grok, and also the QN, and also DeepSeek models. On the other side, when we take a look at what happens on the hardware, for example, like a CPU in this kind of scenarios, what we observe is that over the recent years, this kind of CPU, in terms of its performance, they are increasing, their performance increase largely minor, which means they are changed slightly. But more promisingly, when we take a look at what happens on the dedicated accelerator, for example, like the GPU, what we observe is that over the recent year, they have achieved evident improvements. For example, typical example are here for the recent generation of GPU like H200 and even the B200. This is a significant increase compared to the CPU, but when we compare against the existing models, we still find that there is a huge gap in between. So key here is that there is a huge potential with GPUs, but there's still a large gap for us to actually harvest the real performance gains when we are facing this kind of large-scale models. Then we would like to think about why there is a gap. So the first thing we identify is that there is a precision mismatch. So essentially is that this kind of high performance GPU units usually comes with limited precision options. And they cannot sufficiently support application with diverse precision demands. Take the example of the GPU stream processor. Here we identify the GPU streaming processor, which consists of different kind of units. And one of its key units called the tensor core units. Basically, it offers several options of this kind of computations. For example, FP16, int8, and int4. Those are focusing on the lower precision scope. But on the other side, when we take a look at what happens on the application side, we will notice that their application could be quite diverse in terms of the precision demands. For example, for scientific computation, we could have a high precision demands, like the FP32 or even higher. On the other side, when we take a look at what happens on the lower precision side, we could have this kind of lower precision quantized deep learning. For example, across different layers, we could apply different number of bits for different elements, like the weights and activations. Therefore, when we try to directly bridge these two together, we found that they are actually mismatched because there is no perfect match in between. The second part of the gap we found is that there could be a compute mismatch in addition to the precision mismatch. Essentially, it is a sparsity. Because the dense regular GPU cannot effectively support applications with diverse inputs, such as the sparse and irregular graphs, and also the attention in the transformer. Take the GPU as example. Here is a stream processor, which has several of the stream processor as we did illustrate in this example. And it usually offers like a trillions of the parallel threads and high throughput, like terabytes of the throughput, and high HBM bandwidth. But in order to saturate this kind of high performance, we need to have a highly regular dense workload. For example, in these cases, we identify the vector multiplication, but in reality, we could also have the dense matrix multiplications, such that they can satisfy this kind of stringent input requirements. But on the other side, when we take a look at that in reality, what we found is that in the real world, there could be a quite irregular input. For example, in these cases, for the graph, we could have an irregular connection between different kind of node pairs. Therefore, they could have the sparsity in their input. And when we try to deploy this kind of workloads towards this kind of GPU units, what we find is that the GPU streamer processor would be quite performed differently from each other. There could be GPU underutilization among different kind of stream processors. Therefore, there could be inefficient processing due to this kind of diverse and irregular inputs. Let's identify the third type of gap. Essentially, there's a memory resource limits. Specifically, the GPU usually comes with a limited memory capacity and cannot easily accommodate diverse ultra-scale deep learning models. For example, let's take a look at a recent generation of the GPUs, like the A100. It comes with 80 gigabytes for the maximum memory capacity, and even the B100, it comes with 192 gigabytes. But on the other side, when we take a look at what happens on the application side, we found that the application usually more resource demanding. For example, the deep learning recommendation models, it comes with extremely large embedding tables. And also for the large language models, it comes with the high memory capacity for their attention computation, and also for the activations, and also the weight parameters. Therefore, there could be insufficient resource capacity when we try to bridge these two together. The last but not least, we should include the human in the loop because there could be diverse user demands. GPUs, usually designed with fixed memories and computing capacities, cannot easily accommodate diverse user requests effectively. For example, once it has been built with this kind of hardware, can only be used as it is. However, when we take a look at the input side, the input could be the text with different lengths. The input could be images with different size and resolutions, and also the input could be the audios with different patterns. Therefore, when we try to directly merge these two together, we will find that the performance would also fluctuate among different kind of inputs. To bridge these kind of gaps, my research basically tried to cover this kind of scopes by focusing on the computation innovations. Specifically, in the initial stage of my PhD research, I was focusing more on the algorithm innovations, basically the model design and also the model poolings by focusing on how to reduce the complexity of the models. And in the middle phase of my PhD research, I was focusing more on the hardware innovations, basically the hardware accelerators. How could we change the hardware in order to fit this kind of high computation demands? And more recently, I was focusing more on the software innovations, basically while focusing on how to bridge the hardware and the software together. I was focusing on the runtime system, also the compiler designs. Let's have a short recap of the overall scope of my research based on these three major directions. Specifically, I was addressing the precision problem by focusing on different types of the precisions and its accelerations on the modern hardware platform like the GPUs. And the second direction, I was focusing on the sparsity issues. Basically, we were focusing on the full scope of this kind of sparsity like computations, including the dense computation all the way to the dynamic sparsity, which is a more challenging settings. And by focusing on these two axes, we actually strengthen the individual capabilities of our systems for efficiency and adaptabilities. And furthermore, we're focusing on the diversity of the platforms by focusing on the single GPU all the way to the hybrid platforms with the CPU plus GPU accelerators. By focusing on those two axes, we actually empower holistic system design with more scalabilities. And my research covers this kind of scope by with an array of the research works. Specifically, we're focusing on precision, sparsity, as well as scalabilities. And some of our work also be adopted by the industry as well. For research impact, my overall research awarded the NVIDIA Grad Fellowship, and one of my work adopted by the NVIDIA Catalyst library. Another one focusing on the sparse acceleration on the GPU Tensor Core was streamed to the sparse TIR in the TVM project. And furthermore, one of the runtime system, by focusing on the dynamic sparsity, will facilitate many other industry adoption and following up projects. Let's start with the first one by focusing on the precision side. Nowadays, there could be diverse precisions for different kind of deep learning applications. And one of direction focusing on the low precision, specifically the lower precision quantized deep learning applications. For example, in this kind of situations, the precision could be quite diverse. There could be 1-bit wait, 2-bit activations. There also could be the 3-bit wait and 4-bit activations. And we will try to offload this kind of workloads towards our GPU devices. What will happen is that we mostly leverage the GPU Tensor Core to perform this kind of computations in a lower precision scope. And one of the typical units like the GPU Tensor Core, they can offer a wide range of the options, but they actually have limited options to handle this kind of diverse user demands. And for example, this kind of demands could be cost layer, where different layer would exhibit different kind of bit precisions. Additionally, the precision demands could vary even intra-layer, where we could have a 2-bit wait and 3-bit activations. Therefore, this kind of lower precision deep learning applications, while it can directly leverage the low precision GPU Tensor Core, for example, when we have 2 bits and 3 bits, we can actually downcast them into the 4 bits to leverage this kind of computation. But there could be suffer low efficiency because when we cast them, we actually introduce additional memory overhead for padding and also extra computation overhead to manipulate additional bits. Therefore, the key challenge here is that how could we actually harvest this kind of real low precision computation benefits? And our solution here is that we can actually do bit decomposition for quantized deep learning. Our key insight is that this kind of quantized deep learning can actually be composed with more basic, for example, like the binary precisions. Here is one example where we have 2 bits and 3 bits precision to perform the quantized deep learning computations, where we have the 3 bits wait, 3-bit activation, and 2 bits waits. In this kind of situations, what we actually do here is that we actually manipulate all the 3-bit activation and the 2 bits waits by decomposing them first into a 1-bits elements, and later on do the cross products and do the reduce and shift, and finally do the accumulation to get the correct outputs. And here, when we do the computation, we actually perform the 1-bit computation on the GPU Tensor Core, where we can actually harvest the real performance scan when we try to leverage this kind of Tensor Cores. But the one thing to know here is that when we do the 1-bit computation, the AND operation is actually intended as an alternative for the multiplication when we're using the higher precision computations. Overall, we achieve a 2.3 time speed up over the Tensor Core design, which is the SOTA design with the coarse grain precision. For example, we leverage the Catalyst into 4 as our baseline for comparison. And this kind of design also has been incorporated in the Catalyst library to composite that irregular bits in their computations. Once we have done this kind of precision part, let's focus in more on the other side, which talk about the sparsity issues. One of the when we think about the sparsity, one of the things coming to our mind is that where the sparsity comes from. Essentially, graphs are a major source of the sparsity, where graphs are pervasive, and graph learning is the key to extract useful insight from this kind of like data structure. And we can easily find its wide spectrum of application across different kind of domains. For example, in our daily life, we could have a friend recommendation, failure detection in power grid. For scientific computation, we can focus on the chemistry, for material synthesis, and also biology for molecular analysis. For typical paradigm of the graph deep learning, we can actually take a look at its major steps. For example, when we try to learn from the useful input, we'll focus on the graph learning layers, which compose of both the graph operation and also the N operations, where the graph operation basically performs the operation on the graph to gather useful information, while N operation try to perform the linear transformation on the collected data. And when we take a look at the model view, where the individual layer of the graph neural network will become the drop-in replacement of the original layer in the traditional DN network. For example, over here, we replace the GN layer with the original like a CN layer or some linear layers. And overall, all other steps are similar. But the input will change because we not only input the dense embedding matrix, but also have the sparse and irregular data graph structures as input. And ultimately, we will do the node classification for node prediction or some other tasks. Then we may think about what's the challenge of mapping this kind of computation towards the dense unit on the GPUs. Specifically, we first abstract this kind of computation from the graph-like operation towards the matrix multiplication, which is generally used in handling this kind of computations. Specifically here, we show a sparse adjacent matrix of a graph. And when we try to do the computation on the dense GPU units, we basically try to capture a window of this kind of non-zero elements and shift the windows either horizontally or vertically. And when we try to do the computation, basically the individual window will perform the following operations, where the adjacent matrix will multiply with the embedding matrix. And ultimately, we will get an updated embedding matrix. And here comes the challenges. When we take a look at what kind of the graph data we have is that even the moderate size of this kind of graph could have exhibited huge memory consumptions if we just store them in the like a dense format. Here, it significantly outfits this kind of modern GPUs. And also, when we take a look at what kind of computation it actually happened, is that when we try to capture them in the dense window size, there is a largely wasted computations, and because there's a lot of zero elements happens when we try to do the computation in this kind of naive way. The question is that the challenge here is that directly mapping of this kind of computation to dense unit will suffer from the extra high memory consumption and extremely low computation efficiencies. So our solution here is that we do a order environment like transformations. Specifically here is that we'll focus on the how to tame this kind of irregularly scattered elements to condense them to benefit high performance GPU units. Specifically here, this is the original sparse matrix of the graph. And we do condense of this kind of graph based on what kind of computation granularity we have. For example, in these cases, we use the 4x4 tile to illustrate this kind of example. And after this kind of condense during the offline phases, we'll basically try to shrink the size of the iteration when we do the computation of this kind of sparse graphs. Overall, we achieve less memory access and also improve the computation intensity and also the efficiency. And overall, we achieve 1.5 to 6 times speed up over the existing SOTA operators from the cuSparse and also the DGL libraries. And this has also been used by the Sparse TIR in their upstream to the TVM project. Here, we address the problems in a relatively simple way because we assume that we know the graph beforehand. But in reality, this kind of sparsity would hardly known before we actually run the execution on the input graph. So then the question becomes, what if the input are dynamic? So our solution here is that we build a runtime system, try to generate the optimized configurable kernel in a lightweight manner for the GN execution on the GPU based on what kind of input we have seen. So the overall idea here is that given the input and also the code we have written in the PyTorch frontend, what we do is that we will take a look at what happens on the input. We will capture the performance critical input factors. And also, underneath of our design, we have our template-centric like design and optimizations. Basically, we structure this kind of parameter and design space, and we also give them a proper like a multi-dimensional design abstraction, and do the hardware-aware design search to explore this kind of structure and parameter design space. And ultimately, we will generate a kernel at the runtime that can automate the input-aware adaptations and to execute on the GPU. Here, we address the relatively small scale settings where a single kernel can actually handle this kind of input. But what if the input, for example, let's say the graph and also the embedding size exceed the size of the GPU GPU devices? What would happen? And how could we scale towards this kind of large input and platforms? Here comes our innovation for heterogeneous multi-GPU workloads and abstract them as a pipeline to handle this kind of ultra large input. Specifically, we treat this kind of multi-GPU workloads as a heterogeneous workload pipeline and to tailor it dynamically at the runtime. Specifically, when we have this kind of large system, for example, like the multi-GPU systems, usually happens is that when we put this kind of workloads towards the individual GPUs, they will not only do the computation, but they also need to exchange information from each other. Therefore, there could be the compute as well as the communications happens among different kind of GPUs. Here we demonstrate the ideal cases when the compute and communication workloads are actually at the same size, at the same scale. But in fact, there could be multiple factors that would affect its efficiencies. For example, we could have like a much slower GPU interconnects. Therefore, we suffer from a higher communication cost versus compute. And when we have a fewer GPU, this kind of communication cost shrinks because we have less data movements. But when we have a denser graph, there could be more compute versus communications, and so on. So what is the essentially change here is that when we change the input and hardware, the essential change is that we change the relative cost of the communication and the computations. And based on this kind of insights, what we want to explore is that instead of changes are how we handle how we orchestrate our hardware runtime, the better way is that can we explore diverse combinations for different kind of workloads. When we try to break them down, we could try to combine them such that they can better overlap with each other because the computation and communication will leverage different kind of function unit on the GPU devices. And when we try to do different combination and later on mix them on the GPU stream processor for scheduling, we are essentially handling this kind of workloads as cocktail, where different ways of the combination essentially is a different ways of mixture. And ultimately, you will get a different output. Based on this kind of insight, what we do is that we build a system to leverage this kind of fine-grained pipelining for distributed GN computations. Specifically, it generates an optimized pipeline by leveraging the input insights as well as the platform specifications. From the left to right, we will ultimately get an optimized pipeline and mappings. And the technique we just introduced, we focusing on the middle part, where the input and hardware are basically orchestrate basically leveraged to orchestrate the pipeline we want to execute. There are some other optimization, including hybrid data placement and specialized memory design and optimizations, as well as the intelligent runtime to gather all these kind of individual components. Actually, are detailed in our paper. But after recapping this kind of prior research, we will also like to discuss some new research directions by exploring the joint optimizations based on the scope area previously explored. Specifically, what we'll focus more later will be focusing on the joint exploration of the hardware and system optimizations. And furthermore, we'll also explore the joint optimization of the algorithm and system opportunities. But how could we approach that? Let's take a look at some details. Specifically, for the new hardware system optimizations, one of our recent work after my PhD graduation, we are focusing on the portability, essentially for sustainable AI, where new hardware system designed to adapt towards diverse real-world application settings. And while my work are focusing on the efficient deep learning recommendation models on the disaggregated memory, for example, the CXL, which is one of the recent communication protocols based on the platforms, where we co-design and co-optimization diverse accelerators and also co-schedule workload with the near data processing as well as the multi-tenant support for to co-locate diverse deep learning applications. Additionally, we will also take a look at the accelerated deep learning with the reconfigurable data flow architecture like the Subnova and many other accelerators as well. And specifically, for this kind of novel accelerators and architectures, we'll be focusing on the combined optimization for data flow design and design space search, as well as the workload-aware runtime adaptations. Additionally, in addition to the performance, we also take a look at the eco-friendly aspects of the deep learning models and deep learning systems on the energy and carbon aware hardware system co-design, where we focus on the dynamic energy scaling to balance the runtime performance and energy cost, as well as the carbon aware scheduling to balance the energy availability and job requirements. So this is for the portability part. Later, we will also take a look at the certification. Essentially, we enclose the human in the loop for human-centric AI, where we have an algorithm system co-design that can intelligently suit the various users' demands. And one of the recent work are focusing on the patch-based diffusion model serving, where we have like a SLO-aware dynamic repatching for efficient parallelism, and also patch-based early exit. Additionally, we focus on the resource-efficient deep learning with the logarithmic number systems by focusing on the dynamic deep learning precisions with multiple base LNS and also memory-efficient models. And we also take a look at some other fancy application by focusing on the text to 3D scene constructions, where the cross iteration spatial and temporal locality was explored for system optimizations. Let's have a short detail some of this patch-based diffusion model survey. Specifically for the stable diffusion model, when we have a random image, what we do is that given a text, we try to do a diffusion and a denoising process to ultimately get a clear image that we want to have based on the text we provided. And the overall process is like this, where we have an encoder part, UNet part, and also the decoder part. And this kind of process will also iterate through multiple different kind of steps. And the number of steps could be like tens of the steps or even reach to 100. And for this kind of diffusion models, our observation is that the diffusion model serving actually have all usually facing a different resolutions. Specifically, when we do a profiling on the recent generation of the SD 1.5 and SDSL on different kind of settings, what I observe is that the request coming to the diffusion model would have the small batch sizes, could hardly saturate the GPU resources. And this kind of input request will also be diverse, where we could have small images interleaved with some other image resolutions as well. Therefore, the request with the different resolution could lead to the sequential processing, because the diffusion model usually customized for individual resolutions. Therefore, the question comes, how could we handle this kind of real-world stable diffusion model serving with diverse resolutions, which is the real-world challenges. And our key finding is that there's some new opportunities where we can use the patch-based resolution for adaptable executions. Specifically, the stable diffusion serving request could come with different resolutions like this that we have captured in the last slides. And what we do here is that we can actually decompose this kind of large resolution one to a small resolution. Essentially, it is a controllable resolution. We can decompose it into a more fine-grained if necessary. And this kind of patch-based resolution adaptability enables the more parallel processing opportunities. And here comes the one typical example is that we can decompose the diffusion the request with different resolution into different patches. And this kind of different patches could be like based on the largest common factors across different kind of requests. For these cases, those kind of requests are decomposed into 4 or 6. But how could we manage this kind of patch-based data layout is one of the key challenges. And we actually introduced a new like a patch-based image representation where we first do decomposition and later on we build an image index based on this kind of a decomposition. And finally, we have our resolution index built on top of the image index to give a more coarse-grained indexing for facilitated computation. The overall strategy is analog is one of the analogy of the graph CSR that we regularly used in our graph processing. And by using this kind of new indexing, we actually have to reload some like common operators in the diffusion model, for example, the group normalization. Additionally, we need to have our new customized coarse attention operators for this kind of patch-based image representation. And later on, when we handle the convolution, because now the images are decomposed into different parts, different small patches, we also need to handle this kind of convolutions specifically because especially when we decompose them, the convolution among the different kind of boundaries should also be considered because those kind of boundary information will be loose if we don't consider their locality. With this kind of patch-based image representation, we enable new opportunities. Specifically, we unified the processing of different resolutions, where different kind of image requests can actually be unified with the unified like this kind of image small patches, and we can do the window shifting among different kind of patches. And later on, we can control the granularity of the mixed workload composition in a more confident way. For example, when you have this kind of different resolution, essentially we can actually patch them together to form a new like workloads that can benefit our overall executions. Additionally, we can also unlock more fine-grained like pipelining because once we have done this kind of decomposition, even though originally there could be a resolution match for the different kind of computations, they are sequentially executed. But now, by performing this kind of decomposition, we can actually perform the more fine-grained batch-based processes to saturate the overall GPU utilizations. So here, let's look back to our like overall like future research. So we have done the certification part, and the last part, also the part we try to extend is the safety part, essentially the trustworthiness of the AI, where we do the confidential and encrypted deep learning model servings, where the holistic scheduling of the encryption and the regular deep learning operation for ultra low cost deep learning model training. Additionally, there is some work that I previously bring up from the intern at Microsoft Research. Basically, we're focusing on the failure resilient collective communications for heterogeneous memory and compute devices, where this kind of protocols can directly recover itself and heal itself once it has encountered some failures, even happened on the hardware. And later on, we also take a look at the efficient watermarking for the intellectual property protected deep learning models, because this kind of computation costs also suffer from a high overhead. Therefore, we could balance the robustness of their watermarking technique as well as their efficiency during the runtime for efficient real-time processing. And I think that's all for my talk, and feel free to ask any questions. Yeah. Any questions here?
Hi, Yuka. And thank you so
Hi.
much for this wonderful talk. And
Mhm.
so I have several questions, but first, so any questions from the audience?
Yeah.
You can either unmute yourself or input your questions in the chat box.
Good morning. Am I audible?
Yes, yes.
Good morning. Thanks for a nice talk. I had a query. What is the way to ensure the testing? What is the testing plan that will ensure that the model is deployable as it is expected to perform?
Oh, you mean the testing plan, the evaluation plan, right?
Yeah.
Asking
The
the
testability of the whatever features which are planned to be incorporated in the model.
Okay. I think
Yeah.
for the talk, based on the talk content, I think for the deployable, I think there is one thing is that, for example, let's take a look at the quantization part, right? Whether it is deployable, I think there's two things we need to consider is that firstly is that what kind of the precision when we apply this kind of quantization and what kind of performance gain we are actually harvest from this kind of quantization when we leverage the tensor core. So this is the precision part. And for the second part is that for the like sparsity part, what I want to say is that what kind of overhead we introduced when we try to do the compression versus what kind of performance gain we get from training this kind of like graph neural network models. So I would say that there is a bunch of an array of the trade-offs when we try to consider when we are facing this kind of like deployment availabilities when we consider both the quantization in terms of the precision efficiency trade-off and also the sparsity in terms of its overhead and the efficiency trade-off. Yeah.
So the outcome of the like let us suppose if we have to measure the efficiency of the compression, for example.
Mhm.
So how do we ensure that all the representative examples have been considered as far as its evaluation is concerned? That how do we make sure?
So your question is that how could we make sure that the compression is actually performs as expected as its initial
Yeah,
design
for variety. Yeah, for variety of inputs,
input,
for
right?
variety of yeah, yeah.
Okay, okay. Actually, I think that's a very good question. Based on our observation, is that, for example, let's take a look at the like, for example, this kind of compression technique, for example, over here, right? So
Yeah.
essentially, for this part, for different kind of input, what we basically take a look at is that what kind of after this kind of compression, what kind of like computation we are saving. For example, when we apply the 4 by 4 to one of the graph, it may not work on the other graph because different graphs they could have exhibit different patterns for this kind of non-zero element distributions. We could potentially apply 8 by 8 to achieve a better efficiency when we have another graph. So for this kind of selection process, I would say that one promising direction is that to apply, for example, the machine learning based like a profiling model or some other like heuristics to find out what kind of best parameter or configuration could actually fit into the individual individual inputs. But for this example specifically, since they are statically applied offline, I would say that there is more room for optimizations. But if it is online, for example, as the example I illustrated here, this kind of sureness is do not exist because we have to consider its runtime overhead. So I think I agree with your suggestion, but I would say that it depends on what kind of input we have, and we need to devise a mechanism to detect this kind of input variations.
Fine. Thank you. Thanks. Yeah.
Yeah. Any other questions?
Any other questions from the audience? Okay, so I will
Mhm.
ask some questions. Yeah,
Sure,
yeah.
sure, sure.
So first, so you work. I know that you work on several projects on those quantized the
Mhm.
work OM. So I
Mhm.
was wondering, so from the perspective of the system designers, so
Mhm.
how do you think about what is kind of the future trend for this kind of quantized
Mhm.
quantizations for the to accelerate or to compress the models? Because we know that so I think right now the server already can achieve like the
Mhm.
4 bits, right?
Yes, 4 bits. Yes.
And then so do you think that it is possible that we can like to target for 2 bits
Mhm.
or even 1 bit? So whether that's already kind of nearly
Mhm.
hit the wall of the quantization.
Okay, the hidden wall, right? The hidden wall.
So we hit the wall, yeah, because
Yeah.
you know
Yeah.
that the limit is the 1 bit, right?
Mhm.
But it's
Yes.
I think it's 1 bit maybe too challenging.
Yeah, yeah, exactly. I think from my recent exploration is that I think for large language model like settings, they have actually there's some work from the Microsoft research. They have done like a 1.5 bits for the large language model, and they observe that for that kind of settings, the large language model can tolerate the accuracy drop or accuracy degradations. They give the number 1.5, which sounds very weird, right? But essentially, they try to apply the quantization across for different quantization for different parts. I would say for the future is that the quantization should not be as uniform as I have introduced here, where we have like 2 bits weights, 2 bits weights, 3-bit aggregation across all the layers, all the elements. But essentially, this quantization could actually be tailored towards what kind of like input or what kind of activation map we could have. I think one of the typical work you can also check is that from the Song Han's lab, I think they have done like AWQ, which is activation aware with quantization or something similar. I think they have done tailored quantization based on the significance of certain elements. So I think those are the more intelligent way to better accommodate this kind of like precision loss. But in order to do that, I think there's a significant system challenge as well, because when we want to achieve that, if we perform it a more fine-grained way, I would say that there would have be like alignment of the data, because across the layers, if you have different data types, there could be a significant challenge when you do the data transformations, because this kind of cost was not supposed to be there, because originally when we have a unified like the data processions, we just handle it smoothly without any considering this kind of additional cost. But if we want to have this kind of new modules or new adaptive quantizations, I think that definitely need to be considered. Yeah.
Okay, thank you so much. And another question is that, so because you once worked as a PhD for 6 years, and then
Yes.
right now you're working in the industry, and you will soon return to the academia as the
Yes.
So regarding the MLC, so how do you think that, so what is kind of the difference, the viewpoint from the academia and the industry? You think
Okay.
what is kind of your vision to the future of the MLCs? Especially we know that right now every day we have many new things.
Yes.
This week is the open source week of the DeepSeek, many things, new things.
Yes.
Right. So
Yeah,
how do you think about it?
Okay, that's a very good question. So essentially, what I observe in the industry is that industry, for example, let's say like Amazon, the group I am currently working at, and I think they are focusing on something like requires more efforts in terms of the engineer side to achieve something different. For example, the group I'm currently working at, they have done something like building a new accelerators. For example, in Amazon, I think they have announced their Trillium as one of their new accelerators to combat with the NVIDIA's GPUs. The reason we want to do that are twofold. I think one fold is that for this kind of new accelerators, it is more simple, I would say, compared to the NVIDIA GPU. They won't necessarily have so much different kind of functionalities, different kind of units. And they are very simple. They dedicated it for the deep learning training, for example, the transformer and also all these kind of transformer related operations. And they are more simple in terms of the design. Therefore, they are more easy to maintain. And the second part is that it mostly comes out from of their business like a goal, because they want to save the cost. Because for the NVIDIA GPU, from my understanding, is that 70% of their cost actually is not related to their manufacturing and all this kind of cost, and which means the price is way more higher than it actually consists of their components. So in this kind of situation, the industry side, I would think they are more business driven, but they try to build something that usually cannot be handled by the academia settings. And in order to accommodate this kind of new accelerator, from my observation is that they actually spent a significant amount of manual efforts. For example, because of these new accelerators, they have to build their own complete top-down compiler stack from scratch, which means they have to build for example, from hardware design, IR design, all the way to the compilation workflow, compilation tool, all the way to the top level, like how to port it to the PyTorch and TensorFlow or JAX, something like that. Therefore, for this kind of efforts, it usually cannot be handled in academia. And for these kind of situations, they have to spend a lot of time and monetary cost. But in academia, I think we have our flexibilities, because we can actually build on something already there, and we can explore something more flexibly, which means for industry, they usually focusing on, for example, for example, the new accelerator project that I mentioned, they are usually limited by their scope. For example, they have to build the combiner based on what kind of accelerator they have. But in academia, I think we are more flexible. We can actually abstract the commonality among different accelerators in addition to those kind of dedicated accelerators from specific vendors. We can build a more abstracted layers such that we can accommodate different backend, and also we can also develop different front end to better fit the user's demands. So I always say that industry is focusing more on the engineer side and also more like labor intensive. But on the academia side, I would say that we are more flexible and we have more opportunities and could have a larger scope when we want to conduct our research.
Thank you so much for this wonderful answer. And just following your response that so because in your slides you mentioned that you previously also worked for a while on the accelerators, but I think right
Yes.
now the main research is on the GPUs or stuff, right?
Mm-hmm.
And so we know that right now, so we have NVIDIA's GPU series, and also we know that as you mentioned that like also the cloud service provider like Amazon, Meta,
Mm-hmm.
Google have TPU,
Yes.
and also like Meta there and
Yeah. They
Google
also have
yeah.
their dedicated MTAI.
So they collaborate with the Broadcom and so on. So for those, so because you are, I think you are system guy, and
Mhm.
so how do you think about that? So from the perspective of the research opportunities,
Mhm.
so we know that NVIDIA already have those ecosystem. All build on that.
Yes.
For
Yes.
those like a more kind of ASIC oriented computing platform, AI computing platforms that so. But you just mentioned that, so Amazon they need to spend a lot of efforts to build an entire brand new
Yeah.
full stack.
Combiner stack. Yes.
Yeah. So how do you think is there any kind of potential research opportunities from the perspective of academia to help to grow the ecosystem for those non-NVIDIA
Mhm.
platforms and so on? So if you
Yeah.
track to those kind of AI ASIC hardware, kind
Yeah.
of array or something like that.
Yeah, I think there is definitely is, and for example, like the Amazon in terms of their like Trinium accelerators, they actually try to send the credits, which is awarded the credits to the research labs. They said that they will credit like 100. I think there are like almost like millions of the credits to the research lab to let them to participate in this kind of campaign for public to commercialize or to like commercialize their like accelerators. So they are taking that efforts, and they also have the session on the Arts Plus incoming this year to have their like accelerator as a like a context to how to program their accelerator to achieve a better speed ups. They will award them some money, something like that. But besides that, I would say that for this kind of accelerators, I think we should focus on something they are in common. For example, for all these kind of accelerators, most of them are focused on the systolic array-based design because for most of these kind of like accelerators, they are handling the task or workloads related to the general matrix multiplications, either in the transformer model, linear layer, and also the convolution layer. So they are mostly focusing on this kind of very common like architecture design. And additionally, they also try to build some like a unified interface, or at least at the current stage, they expose their framework towards like the JAX or some other like a PyTorch for this kind of computations. But I would say that for our researchers, I would say it's better to have if we want to learn something or like build something. I think starting from the top will also be one of the good options because this can free us from the like very complex or involved like low-level hardware details, and also we could take a look at the opportunities based on the like their high-level like IR, for example, either JAX or the PyTorch in terms of the intermediate like execution graph, such that we can first perform some like a graph level like or IR level like transformations before dumping to the diving into the detailed complex hardware execution flow. And but I would say that knowing or learning the detailed hardware characters is also important because they will inform us to perform. How could we perform the transformation on the high level? So we can actually learn these properties and before we performing the transformation on the high level. But later on, we can doing a top-down, like a top-down optimization manner, such that we can lowering this kind of IR all the way to their low-level like execution instructions. So I think overall, from the research side, we can consider how could we capture the abstraction, common abstraction, which is applied across different kind of accelerators. But also, we for researchers, we can also categorize or like summarize their hardware profile, which means their hardware characteristics, to make it aware or inform our system level optimizations. So those are the viable solutions, I would say.
Thank you so much.
Mhm.
Yeah. And any other questions from our audience?
Yes.
No more questions. So if no more other questions, I think I will ask the last question. So
Sure. Go ahead.
so I think you may know that. So I think recently, so NVIDIA just announced that. So they try to use those like DeepSeek R1 to help them to write the kernel codes of the CUDA.
Mhm.
Right? So how do you think about this?
Okay, yeah, I think that's a very good question. Even though I personally I haven't done quite a lot of works for the large language model for code, but from what have known is that for this kind of directions, currently what I know is that for this kind of large language model for code, they are excelled at some settings. For example, they have a very good advantages in the Python like code. For example, they write a Python code, as you can also tell from the code palette you are using currently on your VS Code, and they are very good at writing the Python code, especially for the like PyTorch or NumPy or whatever, because this kind of code base they have been trained on have a lot of code, have a significant amount of code, so they are better at this kind of coding. But when it touched to a low-level code, for example, like the C++ or like this kind of CUDA or CUDA C, I would say that this part of maybe not as good as their Python counterparts. So I would say that for this kind of a kernel level code, I think there could be some reasons because for Python code, they are executed as it is. For example, when we write a Python code, they will basically execute what the code we have written. But when we try to take a look at the CUDA code or even C code, there could be some problems because this kind of CUDA code or Python or like a C++ code, they could not usually can execute it by themselves. There could be like a different like a header inclusion, and also some like a header file and source file separation. And also there could be like a kernel code and the system code. For example, the CUDA code usually driven by the C++ code on the surface to drive them executed on the GPUs. So this kind of separation created the challenges for this kind of code exclusions or code composing on these kind of large language models. But I would say that there could be some opportunities because for the Kotlin-based libraries, they have some very well-shaped, I would say well-shaped like templates because they have like a very well-defined like a WAP level iterators across different kind of memory hierarchies, like the WAP level or computation hierarchies, like the thread level or WAP level, like a block level, or even like a device level. So I think for this kind of well-shaped templates, I think they could perform better. But for the code that you want to directly to run them on the individual like a standalone like a CUDA or C++ project, I think there could be some challenges. The reason is that they may lack of context unless you let the large language model see the overall project about all its source file. I think that would be a good potential improvements, and it could be improved by the things like the retrieval augmented generation, I think. But that is more challenging because the context is also very large, depending on what kind of code it has among different files. And they also need to figure out how to write up the final makefile or CMake or Ninja for this kind of compilation. Yeah.
Thank you so much. The So let's thank our speaker again. So Yuka, thank you so much. So this is a very, very wonderful and informative talk. And also thank everyone to attend our this week seminar talk, and see you next time. And Yuka, so hopefully to see you in the near future. Okay.
Okay, sure. Sounds good. Thanks for hosting me. Yeah.
Thank you. Bye.
Bye. Bye.